Welcome. Let me talk about the conjecture in graph theory, the Brouwer conjecture. I think a method which I've used for an upper bound theorem on spectra of quivers works also here. Like in that paper, it's crucial to extend the result, make it more general, harder by including also loops. Original conjecture is about finite simple graphs, but it works for any finite simple graph with eventual loops. Let's just look at the proof. So one of the main ideas is to reduce the number of vertices and then use induction. When we have a graph with n vertices, we get to a graph with n-1 vertices by removing one of the vertices. Now, what I will have to assume for the induction step is that we have no loops here. But then there is a lemma which allows us to remove loops. Now, if we have no loops, what we do is we take this connection and snap it to the adjacent vertices. So what happens is that the number of edges stays the same, so the m stays the same, but that's the key. The new Kirchhoff matrix is now a principal submatrix. So if these had no loops, these will have loops. So we have to be in a class of graphs which allow loops. And then if you have a principal submatrix, we can use the Cauchy interlacing. The Cauchy interlacing will prove it immediately for k goes to 1 from 1 to n-1, because these are the old spectral data, and then which then kind of majorize the new spectral data. But then we have to fix it for lambda n for estimate, which uses the one-form Laplacian. One-form Laplacian is essentially isospectral to the Laplacian, and Laplacian is here FTF, and here we have FFT. So they're essentially isospectral, meaning that the eigenvalues which are non-zero are the same, so especially also the trace is the same. And for k equal to n, we have just a trace. So the trace is also the trace of k prime, and the trace of k prime is bounded above by n plus n times n plus 1/2. So this is the induction proof. Now there is some work to be done to be able to remove a loop. And if we remove a loop, we just decrease the spectrum. But how much does it decrease? And in order to quantify that, we have to use kind of elementary perturbation theory for symmetric matrices, and that's what the Hadamard first variational formula is for. So if you have a symmetric matrix and we add T times another symmetric matrix E, which is fixed, then the eigenvalue lambda paired with an eigenvector V depends on time. So we have a lambda t curve and a vt, and then we can write down what actually this differential equation. So the eigenvalue changes. This is just by differentiating the eigenequation, equation for the eigenvalue, and using that the eigenvector has length 1. That's the sums of eigenvalues also cannot grow more than 1. So what happens is if you add one more loop, you add here 1, because the loops are counted, and here you add something less or equal than 1. So the statement also holds true if we add one more loop, and we can continue to add more loops, and we have that statement here. If that statement holds for finite simple graphs, it holds also for finite simple graphs with an arbitrary number of loops. So, and that's kind of needed then for the induction step. In the induction step, we just need one vertex which has no loops. If we if we remove that, we cut that away, we have to have no loops here. Then these connections here go here, and the M stays the same, and what eigenvalues of this matrix are. This is bounded above by the eigenvalues of the mu, except for the last part, where we have then to use the estimate for k equal to n. Also for the induction foundation, n equal to 1, we have just, for n equal to 1, we have just a point with possible loops, and in this case the assumption holds. It's actually not even sharp. That's all for today.